Differential privacy has become a standard mechanism to protect data records by injecting noise into data requests, safeguarding individual privacy during exploration. However, this protection comes at the cost of limited flexibility in data exploration due to the finite privacy budget and uncertain feedback from data requests. To address these challenges, researchers Xumeng Wang, Shuangcheng Jiao, and Bryan propose Defogger, a visual analysis approach that facilitates data exploration of sensitive data protected by differential privacy. Defogger provides a visual interface for users to specify data information of interest, describe available data facts, and declare data requests. A reinforcement learning model is utilized to recommend diverse exploration strategies based on the user's exploration intent, enabling users to develop effective strategies within the limitations imposed by differential privacy. A novel visual design is integrated to represent uncertainty in correlation patterns, allowing users to understand the impact of differential privacy on their exploration. The researchers conducted a user study and 2 case studies to demonstrate the effectiveness of Defogger. The results show that Defogger facilitates the development of exploration strategies that meet user requirements, despite the limitations imposed by differential privacy. By leveraging reinforcement learning in visual design, Defogger enables users to navigate the trade-off between data utility and privacy, ultimately enhancing the exploration of sensitive data. The Defogger approach consists of 3 main components: a visual interface, a reinforcement learning model, and a visual design for uncertainty illustration. The visual interface allows users to specify their exploration intent, while the reinforcement learning model recommends diverse exploration strategies based on the user's input. The visual design represents uncertainty in correlation patterns, enabling users to understand the impact of differential privacy on their exploration. The researchers highlight the significance of Defogger in facilitating effective data exploration under differential privacy. By providing a visual interface and leveraging reinforcement learning, Defogger enables users to develop exploration strategies that balance data utility and privacy. The approach demonstrates the potential of visual analysis in enhancing the exploration of sensitive data, and the researchers suggest that future work could focus on extending Defogger to support more complex data types and exploration scenarios. Differential privacy (DP) poses significant challenges for data exploration processes, particularly exploratory visual analysis. The injected noise can mask visualized patterns, lead to high uncertainty, and be difficult to predict. To address this, a novel workflow is proposed that considers budget allocation not only as numerical calculations of noise size but also as a question of which responses actually merit spending the budget. This approach provides recommendations modeled on a combination of user exploration interests, knowledge of data patterns, and an understanding of how a group of data requests can contribute to the exploration process. The pipeline extracts data patterns at different granularities and leverages these to suggest responses tailored to an appropriate level of detail for visualizations that still successfully support exploration but spend budget more wisely. The pipeline is implemented in an interactive tool called Defogger, which interactively recommends feasible exploration strategies for the next step using a reinforcement learning model. Defogger demonstrates how each strategy will work before actually applying the step, improving returns on investment of privacy budgets through intelligent recommendation of data requests based on user exploration intent. This work intersects with existing research in exploratory visual analysis, differentially private publication, and visualizations for uncertainty representation. In exploratory visual analysis, iterative interactions with data are used to inform recommendations for the next visualization. However, existing studies do not consider privacy issues during exploration and recommendation. In differentially private publication, trading schemes consisting of the group of trading targets and how much of the privacy budget should be spent on each target are developed. Existing studies proposed examples of trading schemes and provided tools for scheme assessment. Visualizations can facilitate understanding of uncertainty by demonstrating the existence of uncertainty in data distribution and representing the features of uncertainty. Key takeaways from this research include the importance of considering budget allocation as a question of which responses merit spending the budget, and the effectiveness of combining user exploration interests, knowledge of data patterns, and understanding of data requests to inform recommendations. Limitations of the current pipeline and defogger designs include the need for further evaluation of the effectiveness of the reinforcement learning model and the potential for improved performance through incorporation of additional data patterns and exploration strategies. Future work in this area may include exploring the application of this approach to other domains, such as healthcare and finance, and investigating the use of alternative machine learning models to improve the accuracy and efficiency of the pipeline. Differential privacy, DP, is a critical aspect of data visualization, particularly when dealing with sensitive information. Effective visualization techniques are essential for uncertainty analysis, as they enable users to understand the probability distributions underlying the data. Building on previous work that instantiates data with uncertainty, the authors propose a mosaic design that embeds visual representations of uncertainty into heatmap matrices. In the context of DP, users need to explore tabular datasets while maintaining privacy safeguards. The primary research question is how to optimize the visual exploration process while protecting sensitive data. To address this, the authors formalize the privacy-aware exploration practice, outlining a virtual use case that illustrates available exploration schemes and user requirements. The use case scenario involves a medical analyst, Lucy, who wants to identify living habits that decrease the risk of type 2 diabetes. With a limited privacy budget, Lucy must strategically request data attributes that are most likely to reflect disease prevention. This scenario highlights the need for users to negotiate with the DP mechanism to obtain more accurate data distributions. The requirement analysis reveals two primary impacts of privacy restrictions on visual exploration: increased cognitive energy when formulating data requests, and uncertainty in each exploration result due to noise. A pre-study with DP experts was conducted to understand how a visualization-driven approach can mitigate these impacts, refining specific requirements for each impact. The results emphasize the need for users to coordinate data requests, assess the effect of noise on calculated distributions, and balance the trade-off between data accuracy and privacy. The mosaic design aims to address these challenges by providing a visual representation of uncertainty, enabling users to better understand the probability distributions underlying the data. By embedding uncertainty into heatmap matrices, the design facilitates more effective visual exploration and decision-making under uncertainty. This section of the research paper presents a pipeline for visual exploration of datasets protected by differential privacy, DP. The pipeline is designed to meet the requirements outlined in Section 3.3, including providing effective recommendations for exploration strategies and understanding the uncertain effects on exploration results. The pipeline consists of several steps, as depicted in Figure 3. Initially, users specify their exploration intent, which can be described as distributions of interest, such as the distribution of a single attribute or joint distributions of multiple attributes. A recommendation model then takes this input into account to yield suggestions for exploration strategies. This model employs a graph model to describe multiple data distributions, where nodes represent distributions of single attributes and edges represent correlation distributions of two attributes. The graph model constructs an intent graph based on the exploration intent reserved by users. It then enumerates strategy prototypes by identifying groups of attribute sets that can generate feasible groups of set division schemes. To focus on effective strategies, the model utilizes a reinforcement learning approach trained by Q-learning. The exploration strategy is described as making a series of actions, where each action describes a data request with a privacy budget to be paid and an employed set division. The incentive mechanism for an action is based on three considerations: users' preference for accurate illustration of the exploration intent, the importance of hubs in the intent graph, and the saved budget for further data exploration. The accuracy calculation is based on two types of relative errors: structural errors caused by inconsistent set division and numerical errors led by noise. The model quantifies accuracy according to these errors and assigns a bonus for budget savings. The implementation details of accuracy calculation, data simulation for accuracy estimation under the privacy limitation, and calculation of the bonus for budget consumption are provided. The pipeline also allows users to browse feasible set division schemes for data exploration and test each of them by simulating the data request on simulation data constructed by all known data facts. Users can further examine the feedback and browse possible distributions of the actual data calculated by randomly removing noise. This approach aims to provide a comprehensive framework for visual exploration of datasets protected by differential privacy, enabling users to make informed decisions about their data exploration strategies while minimizing the impact of noise and uncertainty. Defogger, an interactive data exploration tool, facilitates user navigation and understanding of data under differential privacy constraints. The interface consists of three components: information reservation, data request declaration recommendations, and uncertainty illustrations due to noise. The information reservation view displays data exploration progress by visualizing user intent and known data facts. This is achieved through an intent graph, where nodes represent attributes of interest and edges symbolize correlations among these attributes. Node stroke color differentiates between sensitive and public attributes, with dark gray lines indicating known data facts and light gray lines representing simulated distributions awaiting exploration. After a data request, the distribution is updated with a dark gray line, and the width of this line represents the 95% confidential interval, highlighting uncertainty in the requested results. The interface also features a sketch exploration intent capability, allowing users to drag and drop attributes of interest to specify exploration targets. Users can click on dashed edges to indicate interest in correlation between attribute pairs, with all blue nodes and solid lines considered as data facts to be explored. To estimate exploration progress, users can input a value as the estimated rate of exploration progress after the current exploration. This is used to calculate a bonus for budget consumption, quantified by the equation BBC equals WNP plus 1, 2, P epsilon total epsilon remain, where epsilon total and epsilon remain are the total and remaining privacy budget, respectively. N is the number of records in the database, and W is an empirical parameter used for bonus weighting. The default value for P is set at 100%, indicating that it is feasible to spend all remaining privacy budget to satisfy the specified exploration intent. The system's primary objective is to satisfy user intent by allocating the privacy budget for data requests and updating the lower bound of the estimated rate accordingly. To facilitate data exploration, the system generates data simulations of joint distributions, assesses the accuracy of feedback, and recommends data requests. Users interact with the system through three views: data request declaration, uncertainty illustration, and intent graph. In the data request declaration view, users declare data requests and view suggested exploration strategies, along with the total privacy budget required. Each strategy is summarized by an overview glyph that annotates the attribute sets used in each data request on the intent graph. The uncertainty illustration view enables users to understand the uncertainty in the responses to data requests. The system integrates visual designs for uncertainty into histograms and heatmap matrices. Histograms display error bars to annotate the range of 95% confidential intervals, while heatmap matrices use a mosaic design to represent uncertainty. This design divides two triangles from the upper left corner and lower right corner of a grid to visualize the upper and lower bounds of the confidential interval, respectively. Users can filter data records by applying value-based filters of attributes used to specify set division in data requests. They can also browse possible instances of data distributions inferred by the feedback and review the summary of requested results in a matrix. The system allows users to switch to a noise-removed mode to generate new instances of data distribution. The system's effectiveness is evaluated through a user study with two case studies, Tom and Susie, to assess the proposed approach. In the realm of data-driven marketing, identifying target clients who are willing to pay high premiums but claim small reimbursements is a crucial task. This paper presents an innovative approach to achieve this goal through progressive data exploration, leveraging the power of differential privacy. The study begins by constructing an intent graph that specifies the exploration goals. The graph includes attributes such as claim_amount, CLTV, customer lifetime value, and policy type, which are interconnected to form a complex network. To initiate the exploration process, the authors manually declare data requests with specified privacy budgets. These requests are then submitted for analysis, and the results guide further refinement of the exploration intent. One of the key methodologies employed in this research is the use of progressive data exploration. This approach involves iteratively refining the exploration intent based on the results obtained from each data request. By doing so, it addresses the limitations of initial knowledge about sensitive attributes and ensures that accurate data simulation is achieved. The authors also highlight the importance of understanding correlations among attributes. For instance, they found that clients who activated policy B were more likely to have a smaller claim underscore amount than others with similar CLTV. This finding was considered reliable despite slight uncertainty in the data pattern. Moreover, the study demonstrates how demographic information can be used to understand risks of hepatitis B using the National Health and Nutrition Examination Survey dataset. The authors constructed a star-shaped graph with hepatitis_B as the center and explored correlations between demographic information and the risks of hepatitis B. The paper concludes by emphasizing the significance of accurate data simulation for effective suggestions in exploration strategies. However, it also acknowledges the limitations of the approach, including the need for prior knowledge of sensitive attributes and the uncertainty in data patterns. Future work should focus on developing more robust methods for data simulation and addressing the challenges of uncertainty in data patterns. The data request process in the context of differential privacy (DP) is a critical aspect of exploratory data analysis. Table 2 presents a list of partial demographic attributes in the database of survey results, including hepatitis_B, family_C, children_C, teenager_C, and elder_C. The distribution of hepatitis_B is based on the official data from the World Health Organization, which reports a disease proportion of 10.5%. To simulate the data request process, a hypothetical user, Susie, uses the Defogger system to explore the correlation between hepatitis_B and family_C. The Defogger system employs DP to ensure the privacy of the data, generating noise that makes it challenging to identify trustworthy correlation patterns. Susie uses the system's recommendations to determine the attribute groups for set division and the privacy budget. She then simulates the data request and checks the results, finding that the noise generated by DP affects the statistical results of different sets unevenly. The uncertainty illustration view shows that the size of the triangles in each grid indicates the effect of noise on the statistical results. After considering the limitations of her privacy budget, Susie decides to focus on the correlation between hepatitis_B and family_C, using a data request that employs two attributes for set division and spends her entire privacy budget. The resulting visualization shows a more skewed distribution of hepatitis_B than the simulated data, and Susie is able to identify a preliminary correlation pattern. Further verification of the pattern is conducted by switching to the noise-removed mode and exploring the actual data. The results confirm Susie's preliminary conclusion, suggesting that individuals living in big families may have a lower risk of hepatitis B than those living alone. A user study was conducted to evaluate the feasibility and usability of the Defogger system. 10 participants with a graduate-level course in data visualization and experience with interactive visual analysis tools participated in the study. The participants were given a tutorial on Defogger and then explored two databases using the system. The results show that the participants were able to use Defogger effectively to explore the data and identify correlation patterns. However, some participants expressed concerns about the complexity of the system and the need for prior knowledge to specify a reasonable distribution for simulation. Overall, the study suggests that the Defogger system can be an effective tool for exploratory data analysis in the context of DP, but may require further development to improve its usability and user experience. Key findings from the study include: the Defogger system can effectively facilitate exploratory data analysis in the context of DP. The system's uncertainty illustration view helps users understand the effect of noise on statistical results. The attribute groups for set division and privacy budget recommendations facilitate the data request process. Limitations and future work include: the complexity of the system may require further development to improve usability. Further research is needed to improve the effectiveness and usability of the Defogger system. Participants expressed concerns about the need for prior knowledge to specify a reasonable distribution for simulation. Key terms and concepts: differential privacy, DP, noise generation in DP, attribute groups for set division, privacy budget, uncertainty illustration view. Defogger is a novel visual analysis approach that leverages reinforcement learning to recommend exploration strategies based on users' intent, while illustrating uncertainty in data distributions through various visualizations. This system aims to facilitate valuable discoveries from sensitive data, adhering to differential privacy (DP) constraints. By integrating a reinforcement learning model, Defogger balances visual complexity with situational awareness, ensuring that users can effectively explore data while maintaining privacy. A user study and 2 case studies demonstrate Defogger's effectiveness, highlighting key insights. Firstly, the importance of balancing visual complexity with privacy-based situational awareness is underscored, as users must navigate complex data visualizations while adhering to DP constraints. Secondly, the role of experienced data explorers in steering the exploration process is emphasized, as their expertise informs the recommendation model. Lastly, the need for integrating user knowledge into strategy customization is highlighted, as users' domain expertise is crucial in refining exploration strategies. The Defogger system consists of a reinforcement learning model that recommends exploration strategies based on users' intent, which is inferred through their interactions with the system. The model is trained on a dataset of user interactions, allowing it to learn effective exploration strategies that balance visual complexity with privacy-based situational awareness. The system also incorporates various visualizations to illustrate uncertainty in data distributions, providing users with a comprehensive understanding of the data. Future research directions include improving the recommendation model's efficiency and enhancing the usability of the system for a wider range of users. By refining the model and expanding its accessibility, Defogger can support a broader range of users in making valuable discoveries from sensitive data, while maintaining adherence to DP constraints. This page presents a comprehensive list of key research papers and studies that have significantly contributed to the advancement of artificial intelligence, machine learning, and deep learning. These papers are categorized into various subfields such as neural networks, reinforcement learning, and unsupervised learning. The first section focuses on neural networks, which are fundamental components of deep learning. It includes seminal works by researchers like Yann LeCun, David Rumelhart, and Geoffrey Hinton, who introduced the concept of backpropagation in the 1980s. This method revolutionized the field by enabling efficient training of multi-layer neural networks. The next section delves into reinforcement learning, a paradigm where agents learn to make decisions based on rewards or penalties received from the environment. Papers by Richard Sutton and Andrew Barto are featured prominently, as they laid the foundation for this subfield with their work on temporal difference learning and Q-learning algorithms. Unsupervised learning is also covered extensively, highlighting the importance of self-organizing maps and autoencoders. These models allow machines to discover patterns in data without explicit labels or supervision, a crucial step towards true artificial intelligence. Other notable sections include natural language processing, which showcases the development of transformer models and their variants, and computer vision, featuring breakthroughs in convolutional neural networks and object detection architectures. This list serves as a valuable resource for researchers and practitioners in the field, providing an overview of the historical progression and current state-of-the-art techniques in AI and related disciplines. Recent advances in differentially private data synthesis and visualization have demonstrated significant progress in balancing data utility and privacy in various applications. The works of 4044 showcase a growing interest in developing methods for private data publishing and analysis, with a focus on differential privacy as a rigorous standard for privacy protection. Privson, 40, presents a differentially private data synthesis approach that preserves the statistical properties of the original data while providing strong privacy guarantees. This is achieved through the use of the Laplace mechanism, which adds noise to the data to prevent individual records from being identified. Chartseer, 41, introduces an interactive visual analysis system that integrates machine intelligence to facilitate exploratory data analysis while maintaining user engagement and analytical focus. This system leverages the exponential mechanism to ensure differential privacy in the visualization process. DP-Vis Creator, 42, proposes a novel approach to incorporating pattern constraints into privacy-preserving visualizations via differential privacy. This enables the creation of informative and private visualizations that preserve the statistical properties of the original data. The authors of 43 highlight the importance of modeling and leveraging analytic focus during exploratory visual analysis, emphasizing the need for more sophisticated methods to capture the nuances of human analytical behavior. A comprehensive survey by Zhu et al. 44 provides an overview of differentially private data publishing and analysis, covering various techniques and applications. The survey highlights the challenges and limitations of existing methods and identifies opportunities for future research. The equations and algorithms presented in these works are primarily focused on differential privacy, employing techniques such as the Laplace mechanism and the exponential mechanism to achieve differential privacy. The figures and tables in the cited works provide visualizations of the proposed methods and their evaluation results, illustrating the effectiveness of the approaches in preserving data utility while maintaining strong privacy guarantees. For instance, the results of Privson demonstrate that the synthesized data preserves the statistical properties of the original data, while the visualizations in Chartseer show that the system can effectively facilitate exploratory data analysis while maintaining differential privacy. Overall, these works demonstrate significant advances in differentially private data synthesis and visualization, but also reveal the need for further research to address the challenges of balancing data utility and privacy in various applications. Future work should focus on developing more sophisticated methods that can capture the nuances of human analytical behavior and provide stronger privacy guarantees.